Good morning, my dear students. Welcome for the second lecture on chapter waves. In the last class, we have discussed up to progressive wave, differential form of progressive wave, and relation between particle velocity and wave velocity. Now, let us come to an important derivation. Let us derive the expression for the speed of transverse waves on a uniform string. A string is a cord whose length is very large compared to its diameter. For example, a metallic wire, thin wire, stretched between 2 points can be called as a string. It's a cord whose length is very large compared to its diameter and which is perfectly uniform and flexible. When a string is stretched between 2 points and is pulled in a direction at right angles to its length, transverse vibrations are set up in it. The particles vibrate perpendicular to its length, and movement is handed over from one particle to another along the length of the string. That's how the transverse vibrations will travel along the string. A transverse wave travels along the string with a velocity depending upon certain constants of the string. Now let us come to the derivation part. In case 8 marks question, if it is asked on this derivation, you can start from this diagram. So consider a part of the wave AB. Look at the figure. AB represents a portion of the vibrating string. So consider a part of the wave AB traveling in the string from left to right with a velocity v. We want to derive the expression for v. If the string is pulled from right to left with the same velocity, the wave AB will remain stationary with respect to the paper in space. That means two exactly identical waves traveling in the opposite directions get superimposed on each other, produces standing waves. So then AB represents a portion of such a standing wave created on a stretched string. So here AB is a portion of the wave which is created on a stretched string. Now look at the figure. So P and Q are 2 points selected on the wave which are equidistant from the center. So if you join, so AB is a small section, PQ is a small section of the wave AB whose length is dx. If you draw a line from point O perpendicular to vertical line, then this portion will be dx by 2. Okay, I will come to this diagram, explanation of the diagram. It is like this. Let PQ, look at the figure. Let PQ be a small part of the wave having length dx. So AB is a portion of the wave on the string and PQ is a small part of the wave having length dx of the string. If m is a mass per unit length of the string, then the mass contained in this small part PQ will be m into dx. M is mass per unit length into length of PQ is dx. Therefore, m into dx is mass of the portion PQ of the vibrating string. As the string moves along the circular path PQ of radius r with velocity v, it experiences, look at the figure, r is radius of the arc, PQ is dx, r is radius of the arc, join point P with the center O and Q also with O, OP is equal to R, Similarly, OQ is equal to R, and this angle between POQ is theta, and draw this dotted line which divides the angle into two equal parts, theta by 2, theta by 2. Even this length of PQ will become dx by 2 this side, dx by 2 this side. Draw the tangent at point P and point Q. The tangent drawn will meet at point C in the figure, and T is a tension along the string which is acting along the tangent at point Q as well as at point P. So this angle between the tangent and this horizontal is theta by 2. Even this side the angle is theta by 2. So T is the tension. If you resolve this tension into rectangular components, the component along the negative x-axis is T cos theta by 2, and along this line CO, the component is T sin theta by 2. Similarly, if you resolve the tension T at point Q into two components, the horizontal component becomes T cos theta by 2, vertical component becomes T sin theta by 2. So remember, T cos theta by 2, T cos by theta by 2 at point C, they are equal and opposite. They cancel each other. Whereas T sin theta by 2 and T sin theta by 2 acts at point C along OC in the same direction. Therefore, they get added up. It becomes 2T sin theta by 2. This is a net force acting along the radius of the arc. That means it is acting from C to O, and this will constitute the centripetal force. I will come to that later on. Understand what is there in the diagram. I will repeat once again. AB is a wave on the string. PQ is a portion of the transverse wave along the string whose length is dx, and O is a center. Draw tangents at points P and Q. T is a tangent. T is a tension acting along the tangent at point Q. Similarly, at point P, T is a tangent. T is a tension acting along the tangent. So now if you resolve this T into rectangular components, T cos theta by 2, T cos theta by 2 at point C gets cancel each other because they are equal and opposite. Whereas T sin theta by 2, T sin theta by 2 acts along CO gets added up. So this much you understand from the figure. I will continue with the explanation here. Let PQ be a small part of the wave having length dx of the string. If m is a mass per unit length of the string, then the mass contained this small part PQ will be m into dx. As the string moves along the circular path PQ of radius r with velocity v, it experiences a centripetal force. It experiences a centripetal force. The force acts along the radius towards the center O. This force provided by the tensions along the acting along CP and CQ, let T be the tension at P and Q. Resolve the tensions along CO, and in the direction perpendicular to it, we have T sin theta by 2 and T cos theta by 2. The resultant tension acts along CO is 2T. You just make it 2T. It is not 2 pi. 2T sin theta by 2. Since theta is small, we can write sin theta by 2 as theta by 2. Therefore, the resultant tension becomes, here it is given correctly, instead of pi, you should write T, 2T sin theta by 2, which is 2T into theta by 2. Cancel 2 in the numerator, 2 in the denominator. You will be left with T into theta. This is the resultant tension acting along CO. Let us call this as equation 1. For equilibrium position, this resultant tension provides the centripetal force, which is given by, this is a formula for centripetal force. Fc is equal to mass of the portion of the string, PQ is m into dx into v square by r. Equate this resultant tension to centripetal force. We get m into dx, v square by r is equal to t into theta. So from the figure, arc PQ will be same as arc or this dx arc PU is equal to r into theta. This is theta actually. R into theta, r dx is equal to r into theta. This is just like writing s is equal to r theta. So arc length PQ is dx. It is equal to r into theta. This is equation 4. And now substitute this in equation 4. From equation 3 becomes m into your dx is r into theta into v square by r, I am writing as it is equal to t into theta. Therefore, v square is t by m. Therefore, v is square root of t by m. So thus, the velocity of the wave along the string depends on the tension and mass per unit length. So v is directly proportional to square root of t. T means tension. Capital T is tension in this formula. And small m is mass per unit length. So V is inversely proportional to square root of mass per unit length. So this is a formula which will be asked for derivation in the examination. If the velocity expression is asked, you derive up to this. Next, we can continue with the derivation. We can also derive the expression for frequency of vibration. So here, in case the string of length L vibrates in P segments, so in the figure, number of segments is not shown, only a portion of the wave is shown as PQ or AB. Suppose a string vibrates with P segments. Length of each segment will become L by P, and this segment corresponds to half the wavelength, because in standing waves, you know that length of one segment will be lambda by 2. Therefore, length of one segment L by P is equal to lambda by 2. Therefore, lambda is 2L by P. Now use this formula, velocity of the wave V is equal to F lambda. So F into lambda is 2L by P. Substitute for V is square root of T by M. So then we get F is equal to, you can check after simplification, you will get F is equal to P divided by 2L into square root of T by M. So if the stretched string is vibrating with P number of segments between the end points, fixed points, its frequency vibration is given by P by 2L into square root of T by M. Suppose a string vibrates with only one segment between the end points. It is said to be vibrating in the fundamental mode. Then you put P is equal to 1 in the above formula. You will get fundamental frequency of vibration of a stretched string. That is, F is equal to 1 by 2L into square root of T by M, where L is the length of the vibrating string. T is a tension in the string, and small m is mass per unit length of the string. So therefore, we have come across three important equations here. One is velocity of the transverse wave along a stretched string. V is square root of T by M, that's equation 5. And then if the string vibrates with P number of loops, then length of each loop will be L by P. It should be equal to lambda by 2. Therefore, lambda is 2L by P. And using the formula V is equal to F lambda, we can write expression for F. You will get F is equal to P by 2L into square root of T by M, where P is the number of loops with which the stretched string is vibrating between the end points, fixed points. So if P is 1, then we get fundamental frequency formula that is given by equation 8. So this completes the derivation, one important derivation, main question which will be asked in the exam. Next one is one more derivation. Let us derive the expression for speed of longitudinal waves in fluid. That is expression for velocity of longitudinal waves in a fluid. Remember, fluid refers to gases and liquids. In liquids and gases, we can produce longitudinal waves. So now look at this figure. We have considered a cylindrical cross-section of a fluid as shown in the figure. A, capital A is area of cross-section of the cylindrical portion, and Mn is an elemental portion whose length is delta x, and area of cross-section will be equal to capital A. And this is x-axis, and look at all these symbols here. Mn is the initial portion considered. M dash N dash is a position of that portion after a little time when the longitudinal waves travel along the length of the cylinder due to pressure variations. M will be transferred to M dash, N will be transferred to N dash along the axis of the cylindrical portion considered in the figure. Now, with this diagram in your mind, let us go to the explanation part. We know that only a longitudinal wave motion is possible in a fluid medium. Any gas or liquid can be called as fluid. In fluids, transverse waves cannot be propagated. They travel in the form of compressions and rarefactions. Therefore, only longitudinal wave motion is possible in a fluid. When a longitudinal progressive wave moves in a fluid, the particles of the medium vibrates along the direction of propagation. So, at any instant, the particles are crowded, known as condensation. We call it as condensations or compression, and spread out, known as rarefaction, alternately. Hence, there is a continuous vibration of pressure all along its direction of propagation. It means to say that the longitudinal waves are transmitted as pressure variation along the length of the cylinder. Now, you consider a long tube of area of cross section A, which is as shown in the figure. Let the longitudinal wave be moving in the positive x direction along the length of the tube with a velocity v. Let M and N be two right plane sections of the tube whose positions before the passage of the wave are at distances x and x plus dx respectively from an arbitrary origin O, which is not shown in the figure. So the distance of one plane section M from the origin is x, and distance of N from the same origin is x plus delta x. Therefore, the medium is supposed to move in the negative x direction. Then positions of condensations and rarefactions in the tube will remain fixed with respect to ground. That means you think of stationary waves. The volume of the gas enclosed between M and N is A into delta x, because delta x is the length or distance between the two planes M and N. Area of cross section is A. A into delta x gives you volume of the gas enclosed between M and N. On passage of the wave, let the two plane sections get displaced to positions M dash and n dash respectively. Understand this point very clearly. After the passage of longitudinal wave, which is traveling with certain velocity v, let m be displaced to m dash and n be displaced to n dash as shown in the figure. Say m is displaced to m dash through some displacement y, and n is displaced to n dash through distance y plus dy by dx into delta x. This is a new separation between n dash. Now therefore, the thickness of mn, initial thickness of mn is delta x. New thickness of mn will be m dash n dash. Look at the figure. First you understand this point, then I will continue with the derivation. M dash n dash will be this term y plus dy by dx into delta x plus we should add m dash n. M dash n will be delta x minus y. So therefore m dash n dash value will be this term y plus dy by dx into delta x plus delta x minus y, that is m dash n dash, whereas m n is delta x. If we want to find the difference in their thickness, then we should take this term m dash n dash minus mn. M dash n dash is y plus delta dy by dx into delta x plus delta x minus y minus y. That is a term we should think of. Now I will continue with the derivation here. Here you see on passage of the wave, let the two plane sections get displaced to positions m dash and n dash respectively. Let the displacement of the section m be y, that is from m to m dash, the distance is y. And the displacement of the section n to n dash is y plus the dy by dx into delta x, where dy by dx is the rate of change of displacement with distance. Therefore, increase in distance between the two sections is y plus dy by dx into delta x minus y. After simplifying this, you separate plus delta x minus delta x, it is actually cancelled here, dy by dx into delta x. Therefore, increase in volume of the cylindrical slab or slice of the gas in between them. Increase in volume means this into area of cross section we should write. Please check this relation you will get dy by dx into delta x. So here this term is wrong. Y plus dy by dx into delta x plus dx minus y plus minus dx. So plus dx minus dx will cancel. They have left the term here. So you'll be left with only dy by dx into delta x. Minus y plus y gets cancelled each other. So therefore, increase in volume of the cylindrical slab or slice of the gas in between them is this increase in volume into area of cross section. Therefore, volume strain, you know the definition, increase in volume to original volume. Increase in volume is this term. Original volume is delta x into A. So A gets cancelled each other, delta x gets cancelled each other. You will get volume strain is equal to dy by dx. Let it be equation 1. Let K be the bulk modulus or volume elasticity of the gas and P the excess pressure at section M. Now at M dash we have, from the definition of bulk modulus, K is equal to minus stress is equal to excess pressure P divided by strain is volume strain dy by dx. The negative sign indicates that the excess pressure and the change in volume have opposite signs. If P is negative, the change in volume is positive or volume increases and vice versa. Thus, excess pressure at section M now at M dash is given by, just cross multiply, you will get this P is equal to minus K into dy by dx if the pressure gradient along the x-axis be dP by dx, that is called pressure gradient, pressure change with respect to distance along the x-axis, dP by dx, then we have excess pressure at section B. Now at B dash, it is P plus dP by dx into delta x. Substituting for P, we have this equation 3 substituted here. It is equal to P plus d by dx into minus K into dy by dx into delta x. After simplification, we get P minus K into d square y by dx square. We make it d square y by dx square into delta x. Resultant pressure on the slice of the gas enclosed between M dash and N dash is P minus K into d square y by dx square into delta x minus P. Cancel plus P and minus P, we get this equation 5. Therefore, force acting along the slice of the gas is given by force is pressure into area of cross section. So pressure is this. You substitute this, resultant pressure minus K into d square y by dx square into delta x into area of cross section A. So we know that force F is mass of the slice into acceleration, that is Newton's second law. F is equal to m into A. If rho is the density of the gas, mass of the slice of the gas is mass is density into volume. Delta x into A is volume, volume into density, that is mass. Mass into acceleration is d square y by dt square. So therefore we can write force as delta x A into rho into minus d square y by dt square. From equation 6 and 7, look at equation 6, you have F. Even in 7 you have F. Equate RHS and simplify. You will get d square y by dt square is equal to k by rho into d square y by dx square, or we can write d square y by dt square as k by rho will become v. It is equal to velocity into d square y by dx square. So from equation 8, it is a standard form of differential equation of a wave motion. Just like we write d square y by dt square is equal to minus omega square into y. Similarly, we are writing this equation 8, which is a differential form of wave equation. We can write velocity as square root of k by rho. So here k is the bulk modulus of the fluid. It may be a gas or a liquid, and rho is the density of the fluid. So therefore, the velocity of longitudinal waves in a fluid is given by square root of k by rho. There is a general expression for the velocity of longitudinal wave in a fluid. Later on, Newton suggested that the bulk modulus is equal to pressure of air. He substituted pressure of the gas P in place of K, and he gave a formula which is known as Newton's formula for the velocity of longitudinal wave in a gas, which is V is equal to square root of P by rho. Later on, Laplace corrected Newton's formula and he concluded that the bulk modulus is not just equal to pressure of air because propagation of sound in air is not isothermal, it is adiabatic. Therefore, bulk modulus K is gamma times pressure. Gamma is ratio of specific heat of the gas at constant pressure and at constant volume. Then he replaced bulk modulus K by rho pressure P into gamma, and the corrected formula we call it as Newton Laplace formula, which is not there in our discussion. You can go through the text for that particular portion. And lastly, let us come to the relation between group velocity and phase velocity. Even this derivation may be asked for a 2 marks question. So group velocity and phase velocity, you know what is group velocity and phase velocity. Group velocity is a average velocity with which the particles vibrates. Phase velocity is the rate at which the phase changes with respect to time from point to point. Let me give a break. I will continue in the next session, third session of this particular class.